3.3 Superposition and the Pauli Exclusion Principle, 1924. 3.3.1 Superposition. The superposition principle leads to the probabilistic interpretation of quantum mechanics. The states of a quantum mechanical system form a linear space. Linear space, also called a vector space. Mathematically, a linear space satisfies certain properties. U, v goes to lambda sub 1 u plus lambda sub 2 v linear superposition. U plus v equals v plus u commutative.
U plus open brace v plus w close brace equals open paren u plus v close paren plus w associative. U plus 0 equals u. There exists a zero element identity. Open paren a plus b close paren times u equals a u plus bu distributive property on scalar multiplication. Of bu equals of b times u. A times open paren u plus v close paren equals a u plus a v. 1 u equals u is the multiplicative identity. 0 u equals 0 is the additive identity.
Consider a scalar product. Open paren u over bar comma v over bar close paren equals lambda. Properties open paren u over bar comma v over bar close paren raised to the asterisk power equals open paren v over bar comma u over bar close paren. See the equations. Open paren u over bar comma u over bar close paren is greater than or equal to 0, and when open paren u over bar comma u over bar close paren equals 0, then u over bar equals 0. In analogy to the norm on a space, open paren u over bar comma u over bar close paren equals the metric of u over bar squared. 3.3.2 Pauli Exclusion.
The Pauli exclusion principle is that a quantum state occupancy in systems with identical particles of spin 1/2, electrons, can be either 0 or 1 and no more, due to exclusion. This rule, formulated to some extent in spectral analysis applications in 1924 and earlier, was able to succinctly explain the spectra observed. Later, in 1940, Pauli would extend the spin exclusion principle to a more general spin statistics theorem applicable to the fermion particles and boson particles in general. Further discussion of spin statistics in section 7.3.
3.4 Schrodinger Wavefunction. 3.4.1 Obtaining the Schrodinger equation from correspondence and de Broglie relation. We can obtain the Schrodinger equation from operator substitution, de Broglie rules, in the classical, non-relativistic equation. See the equation. Thus, see the equation. With stationary solution. See the equation. Note the similarity to the electromagnetic field in one dimension, optical analogy. Optical analogy, 1D. See the equation. Becomes
open bracket the fraction with numerator d squared and denominator dx squared minus the fraction with numerator 1 and denominator open paren c over n close paren squared the fraction with numerator d squared and denominator dt squared close bracket times e of open paren x comma t close paren equals 0 implies open bracket the fraction with numerator d squared and denominator dm squared plus the fraction with numerator n squared normal omega squared and denominator c squared close bracket times e of x equals 0. If. See the equation.
Note that duality is not complete. The evanescent electromagnetic wave oscillates as it dampens, while the quantum mechanical wave just has damping. Gaussian wave packet evolution. Suppose we have a solution to Schrödinger's wave equation that consists of a unit norm, Gaussian superposition of wave solutions. See the equation, which can be integrated. See the equations. From this we have. See the equations.
For stationary states and 1D potentials, phi of x is a solution to the Schrödinger equation in a given region, and phi of x and times its times at times boun dA are y times btween times dif of f of erent regions must match. We will examine a number of problems of this type in section 4.3.5 and 3.6.
Canonical commutation relations. See the equation. 3.4.2a More complete Schrödinger equation analysis. The time-dependent Schrödinger equation. See the equation. For conservative systems. See the equation. And a general solution has the form. See the equation. This reduces to a time-independent Schrödinger equation.
The time-independent Schrödinger equation. See the equation. Transmission of particles through potential barriers. Recall the probability current density is related to wave function by. See the equation. Where the absolute value of j goes to sub I equals the absolute value of j goes to sub t plus the absolute value of j goes to sub r, and the standard transmission and reflection coefficients are given by. See the equation.
Motion in a central field. See the equations. Thus, see the equations. Separable potential. See the equation. We can decompose the Schrodinger equation as see the equation and see the equation. Time-independent wave functions, i.e. solutions of the Schrodinger equation, correspond to bound or to unbound states according to whether they vanish or are merely bounded at infinity. In one-dimensional problem, the energy spectrum of bound states is always non-degenerate.
Oscillation theorem. If the discrete eigenvalues of a one-dimensional Schrodinger equation are placed in order of increasing magnitude, E sub 1 is less than E sub 2 is less than ... is less than E ... then the corresponding eigenfunctions will occur in increasing order of the number of zeros, the nth eigenfunction having n1 zeros.
Even function potentials. When the Hamiltonian, see the equation, has a potential that is an even function of x, i.e. v of x equals v of minus x, we have, see the equation, where normal psi of x and normal psi of minus x have same e. This results in two cases.
Case 1, E is non-degenerate. Normal psi of x equals c normal psi of minus x goes to normal psi of x equals plus or minus normal psi of minus x. Thus, the eigenfunctions are either even or odd. If all the energy levels are non-degenerate, then, if we write the energy eigenvalues in increasing order of magnitude, E1, E2, E3 ... the corresponding eigenfunctions will occur in increasing order of the number of their zeros, the function corresponding to En having n1 zeros. Since the even, odd, functions have an even, odd, number of zeros, it follows that the eigenfunctions will be alternatively even and odd, the ground state being always even.
Case 2, E is degenerate. The general solution to h of phi of x equals E phi of x is then, see the equation. Thus, see the equation, where a plus b equals c sub 1 times and times a minus b equals c sub 2. Thus, the two eigenfunctions having the same eigenvalue can be written in the form of a linear combination of two functions of well-defined parity, which are themselves eigenfunctions with the same eigenvalue.
Mean value of dynamical variable. See the equation. Uncertainty relations. See the equation. Note that the relation. See the equation. To show, start with b equals u plus I lambda v ... The time-energy uncertainty relations. Normal delta t normal delta E is greater than or equal to 1/2 lambda has a different interpretation. Normal delta E is the difference between two values E1 and E2 at two different moments of time t1, and t2 open paren normal delta t equals t sub 2 minus t sub 1 close paren, and is not the uncertainty in the energy at a given moment of time. In general, see the equation. 3.4.3 The probabilistic interpretation of the wave function. Let normal psi of open paren r goes to comma t close paren denote the wave function, a probability, density, amplitude for a particle's presence at position, r goes to comma t, where the absolute value of normal psi of open paren r goes to comma t close paren describes the probability density. The Schrodinger equation is then. See the equation. In order to have the interpretation of the absolute value of normal psi squared as probability density, we must have. See the equation.
This necessarily leads us to the study square integrable functions, a set called L2. L2 has the structure of a Hilbert space. From the physical point of view, L2 is too large since wave functions which are actually considered contain properties of regularly. To begin, we consider the psi's which are everywhere defined, continuous and infinitely differentiable. A function that is truly discontinuous at a given point in space, mathematically, would have no physical difference from a similar, not discontinuous potential, since no experiment enables us to have access to real phenomena on a very small scale, say 10⁻30 m. It is also convenient to confine ourselves to wave functions which have a bounded domain, the lab, etc. However it is defined, let's denote by script f the set of psi composed of sufficiently regular functions of L2. Thus, Script f satisfies all the criteria of a vector space. We have a scalar product defined on script f.
See the equation. If open paren phi comma normal psi close paren equals 0 goes to phi and normal psi are said to be orthogonal. The square root of open paren normal psi comma normal psi close paren is called the norm of normal psi of open paren r goes to close paren, then open paren normal psi comma normal psi close paren equals 0 only if normal psi of open paren r goes to close paren is identical to 0. Recall the Schwarz inequality. See the equation.
With equality only if normal psi sub 1 proportional to normal psi sub 2. A linear operator associates with every normal psi script is a member of script f another psi, the correspondence being linear. See the equation. Where? See the equation.
Additional notes. Parity operator pi normal psi of open paren x comma y comma z close paren equals normal psi of open paren minus x comma minus y comma minus z close paren. Multiplied by x op x, x normal psi equals x normal psi. Acting on normal psi script is a member of script f can transform into normal psi script is not a member of script f.
Differential with respect to x op d sub x colon d sub x normal psi equals the fraction with numerator partial differential and denominator partial differential x normal psi. Again, acting on normal psi script is a member of script f can transform into normal psi script is not a member of script f.